Hi, I'm Andy Davidson, founder of Financial Lifecycle Education Corp., a not-for-profit also known as FiCycle. Welcome to part 2 of our discussion of credit scores. We'll be talking about the link between data science and credit scores. And as always, we're talking about how math is related to personal finance. What we'll try and explore through the use of mathematics and data science is the question, am I my credit score? FiCycle is a not-for-profit, as I mentioned, and we're actively involved in combining mathematics and financial education. And our work encompasses research standards, a full course at the level of Algebra 2, various training modules, as well as lessons for teachers to use. If you want more information about us, please use the QR code. In addition, we are developing a specific lesson around credit scores, which this video is part of that development. If you're interested in more information about the credit score lessons, please use this QR code and fill out the attached form. Thank you. So in part 1 of our discussion, we talked about odds and probability and how to relate between them. We looked at credit scores and actual results in terms of delinquencies, that is, borrowers making late payments, and how it was related to the log of the odds, created a linear relationship. And then we looked at a function called the logistic function, which was a way of relating probabilities to log odds. We also looked a little bit at some of the data that we received from Experian, showing sample data of actual borrower performance and an actual credit file. We discussed that in order to turn that data into a credit score, there was a variety of steps that were needed, from identifying dependent variables, developing attributes, doing some statistical analysis, and transforming that output. That was a complicated process. So what we're going to do in part 2 is do a simpler process of looking at a car price and do some of the steps that would involve in creating credit scores to give us a little more introduction to the process. So the steps are going to be identify the dependent variables, that is the Y, create and evaluate attributes, that is the things that will explain the dependent variable. We'll model this time using a linear regression, and we'll assess the model and we'll make some predictions. Well, let's get at it. So we have a simple model here, and we're going to be looking at some car prices subject to some variables. We're going to try and see if we can forecast the price of a car given information about the mileage and the car year. What we've done here is graphed those two variables, price on the y-axis versus the mileage on the x-axis, and the price versus the year of the car. And as to be expected, the more mileage, the lower the value of the car, the newer the car, the higher the value of the car. But when we model, sometimes we don't want to just use the variables in their raw form. Sometimes we want to transform them into better measures that will better correlate with the dependent variable, in this case, car prices. So for example, age might be a better factor to use than the car year, because age is really what's causing the car value to decline, not what the actual year is. And then rather than just looking at mileage, it might be better to look at whether or not the car's mileage is higher or lower than an average car for a car of that age. And that way we can separate the mileage variable from the age variable. In order to do this, we're going to use a linear regression. And many of you have seen the formula for a line as y equals mx plus b, where m is the slope and b is the intercept. Well, basically, we're going to be doing the same thing in a regression analysis, but here we're going to be trying to fit a line through a series of dots or points and find the best fit, with the alpha being the intercept, the beta being the slope, and error being the distance between the line and the actual points. So what linear regression is, we just focus on what the model would predict, which would be shown here, and the actual point. We measure this distance between the two, and then we want to minimize those distances. And in regression, we take the square of those differences, we add them up using this summation sign, which just means take all of the individual distances and we square them, we add them up, And then we're going to try and find alpha and beta to minimize these distances. So you can imagine if you drew a line through here, the distances would be very large. And if you drew a line up here, the distance would be very large. But if you draw a line right through the middle, that's going to minimize the distance. And a regression is a way of minimizing those differences. So we're going to do this in Excel. As I mentioned, we think Excel is a very powerful tool for use by students, and it's also the tool that's very widely used in financial and business applications. So we've created our regression equation, which is A plus B times the age plus C times excess miles. And then we're going to try and find the values A, B, and C that minimize this difference. So here's how we do it in Excel. We take our two independent variables, and then we just create an equation, which is alpha plus B times this column plus B times this column plus C times this column produces a model value, which we compare to the price, and then we get the difference. These are regression parameters. These are the errors. Here's where we sum the squares of the errors, and then we're going to minimize those. And we use Excel Solver to minimize those. And using the Excel Solver, we then find that the price is equal to $21,000 minus the age times this number, minus the excess miles times this number, plus, of course, there's some error. We can then graph for each of those points the actual value and the model value. And we can also say, well, what's the error? How good is that? And in linear regression, we use a measure called R-squared. And it's computed by taking the variance of the errors, that is, these distances here, their variance, divided by the variance of the actuals, which is all of the dots. And this model has an R-squared of 93%, which means that the model explains 93% of the variance in car prices. We can then use this model to predict the value of a car. So Bobby has a 3-year-old car with 10,000 miles fewer than usual. So what's the estimated value of the car? Well, the price is 21. We subtract $1,000 a year, and then we subtract 3.3 cents for every excess mile. And we come up with the value that it's $18,187.85 for this 3-year-old car. Well, is that the price of the car? Well, why or why not? We really don't know much else about the car here, do we? We've only really put in two variables. It may be that this car was in an accident, and that certainly would change its value. It could be in a recently repainted, and it could look really great, and that could increase the value. Or any other number of things could have affected the value of this car relative to just knowing that it's 3-year-old with 10,000 fewer miles than usual. So while this may be a good estimate to start with, we know it's not truly the value of the car. When we start thinking about a credit score, and is a credit score U, I want you to think about the car and whether or not that value of 18,187.85 truly represented the value of that car. So in part 3, we're going to turn to another example of a question of, will I be late to the airport? So anyway, thank you for your attention today. Once again, if you want more information about FiCycle, please use this QR code. We'll see you in part 3.